We ended the session before lunch with VLAN. We're going to talk a little bit about a WLAN as well. And the W is the wireless LAN, so some key points that we already talked about due to questions and stuff. So it's a shared network. So instead of having 100 megabit full duplex on your own, we're sharing whatever bandwidth you get with a WLAN. Today, most likely up to 54 megabits. You're sharing it with every other person on that access point. The access point works more or less like a hub as concerned to the wireless part anyway, and is usually connected then into the wired networks. We use radio waves instead of wire. Because of the way it works, we are half duplex only because we're sharing the bandwidth. Wireless is using carrier sense multiple test with collision detection. Because we're using the same frequency to both send and transmit and receive on, the collision avoidance, you will send a ready to send to the access point, and the access point will reply with a ready, clear to send when you're allowed to send. So collision avoidance instead of collision detection. Still shared media though. Hello. Nu kommer
How does that work if you have overlapping VLANs with your neighbors and
yeah.
work on the same frequency? And I guess we need to.
The different. It depends on the standard. Today is basically 3 different standards, and some of the channels used are overlapping, and some are not. Most of them are overlapping one way or another. So basically, if you're using the same channel, you're all right, but then you're sharing with that user as well. If you have overlapping channel, not the same one, but overlapping, that will really affect you. It will usually be even worse than if you're using the same channel. So one of the things with wireless LAN is that you could have overlapping areas, which will affect you. If you're using the same, you share that bandwidth. If you're using overlapping but not the same, it will be even worse.
If I want to send, I get it clear to send on my own access point as well as the neighbors.
If you're using the same channel, okay. If you're using overlapping, then the frequency area overlaps, but you will still get a clear to send from your access point, even though they might be using that frequency in another channel on another access point, which means that you will get interference, obviously.
How wide is the coverage on this one? How often are neighboring lands actually?
It all depends on, again, it all depends on what kind of wireless system there is, because you will see, I've got some slide on it if I get my mouse working. There are different kinds of standards, and there are also some old ones. Whether you have overlapping or not depends on so many different things. Walls, how the environment looks, what the standard you're using, so what channels you're using, how many output VATs you have, and power on the transmitter and stuff like that. So, I mean, an ordinary wireless access point today might have a radius of, I don't know, 30 meters, something like that. But then it all depends on so many things. You get lots of interference and stuff. So, hard to say. Yeah. Wireless LAN, where we could use in warehousing, retail, healthcare, education, businesses, home. Could be a nice thing if everyone that was on Ericsson could connect to the internet by using a wireless or any other business. We've gone from some low speed in the mid-80s, using proprietary solutions, to some standards today. As you can see, IEEE started drafting in 92 on the 802.11 standard. Now there are different standards. There's A and B that was ratified in late 99, I think. And now there's also G, which is backward compatible with B. They're using different bandwidth, different frequencies to send as well. Today, 54 megabits. Now there are equipment out there that double that by using multiple channels and stuff like that. But 54 megabits and shared.
So is that going to evolve into 11N? That's 4 megabits.
And it's more. It's already pre-standard.
Yeah. I mean, there are lots of wireless standards. I'm not going further into wireless a lot, but a lot of things. There's different things for frequency, using different frequencies and checking frequencies to see if they are free and stuff like that. So what wireless LANs are? They are local, usually, used in buildings or campuses, radio or infrared. Most countries don't require you to use a license for most of the frequencies. And most of the equipment is owned by the customer themselves, so it's Ericsson's network or My Home network or whatever. So when we talk about wireless, usually we don't talk about MAN or WAN network, cell phones, or anything like that. It's not what we mean with wireless. Similarities, they're both IEEE 802 standards. We transmit data using frames. In one way, we're using the one Ethernet, for instance, we're using frames, send them over wire. In this case, we transmit data in frames, but using airwaves instead of that. They both have physical and data link layer. They both use MAC addresses. And on top of it, we might run all the usual applications. So you might run IP with all the IP protocols, IPsec, and all the file transfer, emails, and all of that on top of it. Differences: uses radio waves instead of a physical wire. And we, because of that, got problems. For instance, connectivity issues, as we talked about previously. There are different things that can affect how far you can go. You got coverage problem. You got multiple paths. If you got a big wireless network with lots of ways to go, you got interference and noise from other sources. For instance, one of the bandwidth, one of the frequencies used is the 2.4 gigahertz frequency, which is used for lots of other things. Wireless phones, microwave ovens, and different other things. So lots of interference and noise. And also privacy issues, security issues. The first standard, A and B, used something called WEP. And WEP was, and still is used a lot, but it's not very secure. And because you're sending this through airwaves, well, it's kind of hard to stop the airwaves from going. So you got privacy issues. There's something called war driving you might have heard of, where you drive around in a car with a wireless computer and check. They actually have, kind of funny, they actually have a competition each year. I think it was in Las Vegas or something this year, and drove around for 4 hours and mapped all the different wireless networks that they could reach and whether they were encrypted or not. And I think the winner ended up like There's a huge number of wireless networks now. Anyone living in a flat, just try to take a wireless equipment home, and you can find probably lots and lots of open wireless access points. So security issues is a problem. Also, there is no physical connection, and we got battery-powered equipment in some cases. And there might be some regulations country-wise, license-wise, for using radio frequencies as well. Right. Questions on wireless. As I said, I'm not going into it, but we should be discuss wireless as well as we did the other. All right. OSM module. The OSI module was created by ISO for lots of different reasons, actually. One of the things, the one I'm most interested in, is to have a structure. This OSI model is a generic model for how to send data over a network. And what they did is they've tried to create some logic, some order to the way that things should be done. And one good thing, as you might have already noticed from my teaching the first half of the day, is that one thing that the OSI module gives us is a common reference point, so that I can refer to layer 2 without every time we try to discuss something on layer 2 first have to explain what it is. I can say layer 3, and hopefully you all understand what I mean when I'm saying layer 3. Now, obviously, we have to go through the model before we can do that, so here it is. But it's a way of structuring how data is supposed to flow and what layers are supposed to do what different kind of things. It also helps with lots of other things. For instance, today we're used to having different equipment working together. I might, for instance, have a PC from HP. I might have in that PC a network card from, I don't know, Sercom. I connect it to a switch from Cisco, and I connect that switch to a router from Nortel. And I send it over some network from some other manufacturer. It's all working together, and it's all standard. And one way of helping to do the standards is by creating this OSI module to make sure that we know what's supposed to happen on different layers. Also, it's easier to understand what's happening if you can take it one bit at a time. I don't have to understand everything at once. We can look at layer 1, we can look at layer 2. I can look at switches, for instance, and I can explain for you how layer 2 works. And then once we understand that, we can go on and we can go through layer 3. Also, it helps with involvement of applications, for instance. If I'm doing an application, if I'm programming an application, I don't need to know everything about Ethernet or how the cable is supposed to be or stuff like that. I can concentrate on my application, my part, and then I can make sure that my application is giving the information down to the next layer that he needs. I don't have to care about the lower ones. So I don't have to know about IP if I'm doing a application for some higher layer. It might help me, but I don't have to. Now, the OSI model is a generic model for how data traffic over a network should work, no matter what protocol it is. Now, as soon as you try to do something as general as possible, it's going to end up not working, especially in a specific instance. So The same thing as we have an OSI module, and we'll use that. There's also a specific TCP/IP module, which is more or less the same, but based on how TCP/IP and TCP/IP protocols actually works. And you will see a slide on that in a minute. So 7 layers in the OSI model, from layer 1, which is the most physical one, the one that has to do with cabling and voltage and wires and contacts and anything physical, up through the layers, and at the top there's the application and the actual program running that wants to send data. We'll go through it one at a time. Quickly then, at the bottom, layer 1, physical layer, as I said, has to do with how the wire looks, how the cable looks, what voltage is used. Basically, I used to say that layer 1 has to do with how to send a bit on the wire. How do I send a 0? How do I send a 1? How do I do that on the network cable? How does the cable look? What voltage is used to send that 0? What voltage is used to send the 1? How long do I send it? How do I code it? Stuff that has to do with sending a bit on the wire, one way or another. Layer 2 is called data link, and data link has to do with sending data over a link, one link. So, for instance, sending data from my Ethernet network card to another Ethernet network card on the same link, same local area network. Sending a frame from one PC to another frame, to another PC on the same link. So sending data from that network card to another PC on the same LAN. How to send a frame. It could be an Ethernet frame, it could be a token ring frame, it could be PPP or some other frame. It has to do with sending a frame over one link. Layer 1 and layer 2 is what we use for what I used to call network, or what TCP/IP called network access. What we use for transmission of our frames. Now inside those frames there might be IP packets and stuff. But layer 1 and 2 is the transmission technology, if you like, the frame. Now, if we want to send something from this PC to a PC in Älvsjö or a PC in New York, we're not going to be able to do that over one link. It's not going to be Ethernet all the way to Älvsjö. There's going to be one network here, and there's going to be another network in Älvsjö, and there's going to be perhaps lots of networks in between. Layer 3 has to do with networks and how to route packets from one network to another network and a host on that network. Remember we talked about previously sending IP packets, and I had a slide from an IP packet from one PC to a server on the other side. And we said that it's okay to send IP packets from one IP station to another IP station. We'll encapsulate it in frames as we go along. Now, the frames is layer 1 and layer 2. The IP packet is layer 3. So IP and IP addressing and IP networks are layer 3. It's possible to send an IP packet from this PC to my home PC if I want to, because they understand IP. On the way, I will use different physical media, different data link media to go every single link on the way. All right? Equipment-wise, device on layer 1, the hub, physical only cares about physical signals coming in. If I receive a signal, I will send it out on all ports because I don't know what it is, I don't understand it. It's just a signal. On layer 2, bridges and switches to data. Understand how the frame looks, can interpret, get data from the frame, and is used to sending frames from one network card to another on the same local area network. And IP and routers on layer 3 to route between networks. I'll go through IP addressing and subnetting, all that in a minute. Now, on top of IP, we're going to use, or on top of the network, because this is the OSI module, so not necessarily IP, could be IPX or some other protocol as well. On top of that, we're going to have a transportation protocol. And transportation protocol basically has to do with sending traffic from a specific application on my PC to the relative application on the other host or server. And how do I do that? And how do I make sure that it is whole? Do I get all the pieces? Can I send data now, or do I have to wait? This is what, in the TCP IP world, TCP and UDP is doing. IP is host to host. On the higher level, on the transportation layer, is application to application. So that I allow two applications to talk together. The session layer is doing more or less the same. Session has to do with setting up sessions between hosts and applications. So in the TCP IP world, again, this is more or less TCP work. Layer 6 has to do with presentation. Now, if you, for instance, have a text file on your PC, and your PC is a Windows operation system, it might be an ASCII text. Now, that ASCII text file, when that's saved on your PC, it might be looking one way. If you send that text file to a Unix-based system, he's going to be able to read that, but he might have to save it in another format. Now, the presentation layer is responsible for making sure that the receiving side understand how this is saved. What format is it using? Different on the presentation stuff. On top of that is the actual application. And the application is what's sending the data. It might be your email client, your file client, or your message server, or whatever it is you want to. The actual application. The application layer is also where the user can tell the application where I want this to be sent. So it's where the application interacts with the rest. It's where the application gives the data that I want to send to the network stack. So if I want to send the data, for instance, from host A to host B, the actual data that the application wants to send, that's the important part. It might be your text in your email, whatever it is. Now, depending on the application you're using, that application might want to add some extra information to let the application on the receiving side know what this data is, how it's formatted, who it's from, to, any attachments you might have, where do I find those attachments, stuff like that. Application information. That data then might also need a layer 6 header, letting the other side know how this is formatted, in what way I'm sending it. So the host sending it might add a layer 6 header to be read by the receiving side on layer 6. And then I might add a layer 5 header to let the other side know where in the session am I. Am I setting up the session? Am I sending data? Am I tearing down the session? Where are we session-wise? I might add a layer 4 header to let the receiving side know what application running on this host is supposed to have this. what application is it coming from, and who's supposed to receive it. I might have a checksum here and stuff like that. On layer 3, I might add a layer 3 header telling the other side where it's coming from, what IP address is it going to, stuff like that. What network is it coming from, what network do I need to go to. And then I'll take all of this and I'll send it in a layer 2 frame over the actual network where I'm connected. And that frame, obviously, is going to be sent on the wire as 1s and 0 on layer 1. Now, those 1s and 0s are going to be received on the other side, and I will look at all the headers going up through the network. And every single layer has the possibility to read the header put there by the other side, the sending side, and know what I'm supposed to do with this. Now this is the encapsulation and decapsulation of data frame, or data as it is explained in the OSI module. Now remember that the OSI module is a generic thing. It's supposed to work on all datacom. Yeah.
But if you take it on a telly or a movie,
Yeah.
then you don't have peer-to-peer. I mean, you send something and you don't have
But you're
active receiver. You have a passive receiver, more or less.
Yeah, but that receiver still needs to know what application on that host is supposed to have it. What part is this? Is it encoded in any way? Stuff like that. Is this the sound channel or is it the video channel? I might have synchronization traffic going up on the application layer. Even though I'm not sending and receiving, the sending side might still, even if I have a passive listener, as you say, might still need to put things there to be read by the receiver, even though the receiver might not be sending anything back.
So taking that movie again, the application there is the picture and the application is the sound, and you have to divide those two, or?
Yeah, for instance.
For instance.
So you could have the data here could be different data. There's just one data here, but some of the data might be sound. Another part of the data might be video. Layer 7 header could be telling the other side, this is video, this is sound, for instance.
Isn't it so that the application could be something like Windows Media Player?
For instance.
And you
Yeah.
say, okay, I want to open this file. So you contact the host, and it starts sending you a bunch of packets, frames over, because it can't fit an entire movie into 1,500 bytes. So it splits up the file, it sends them over, you see buffering, which is, it's not worth me showing you 1,500 bytes worth, so I'm going to fill up my buffer with a bunch of files. I will recreate them in the order which they're supposed to be, and then I start showing you. So that's the application layer. The presentation thing says this is how you reconstitute them, correct?
Yeah, exactly. And then you have the lower layers to make sure that I know where to send it. I might be multicasting this if it's a video broadcast, for instance. So I'm using a destination address that is a multicast address. That will tell the routers who to send it to. And the routers is using another protocol, which we won't go into, to know whether there's anyone on his network that's supposed to have this. If it is, I'll start sending it. If it's not, I don't send it. So the different information here being put there by the transmitting side that can be read by, in the layer 2 part, switches on the way. On the layer 3 part, it's read by routers en route to the destination. And the higher levels is read by the receiving host. To make sure that I know what this is and what am I supposed to do with it on different layers. So the different headers is used to let one layer on an TCP/IP stack be able to communicate with the same layer on the receiving side. Right? We'll look at this.
Do you always put in headers or every layer.
No, this is the OSI module. If I would do this TCP, let's say an email. So this is the actual email. Now email is using a protocol, a TCP/IP protocol called SMTP, Simple Mail Transfer Protocol. Now your mail, and depending on your mail client, is going to put a SMTP header on. Your mail application is going to do that. SMTP is using TCP as the transportation layer. So I'll add a TCP header to this. And obviously TCP and SMTP is IP protocols, so I'll add an IP header to let the receiving side know where it's coming from and let the routers know where I want it to go. Now this IP packet, all of it, is going to be encapsulated in a frame. Now leaving this PC, if this is the PC that created the email, leaving this PC, this IP packet is going to have a layer 2 header and trailer, and in this case it's going to be an Ethernet frame. I'll send it if the mail service is on the same network as me. I'll send it to the server. If it's not on the same network, I'll send it to the router. The router will receive this. He will remove the layer 2 frame and the checksum at the end, and we'll go into the IP header and we'll read the IP header, and he'll find out where I want it to go. I'll go into his routing table, he'll find the best match, and he will find where he's supposed to send it. When he's sending it, he will put a new layer 2 frame onto it. Send it to the next router, who will remove the frame, go into the IP header, check it, go into his routing table, find the next hop, send it to the next router. Until I get to the server or whatever is supposed to have this, he will receive the layer 2 frame, remove it, network card, look into the IP header, see that this is an IP address that is for me, so it's mine. He will go into the TCP header, or rather Ethernet if that's what I'm using, will give it to IP. The IP process, the IP part of the IP stack, is going to make sure it's for me and some other things that in there. We're going to look at that. And IP is going to give it to TCP. TCP is going to make sure we're in the right place. It's whole. It's doing flow control and stuff like that. And it will also look at the ports, TCP, IP, TCP or UDP ports. In this case, TCP ports. The port is going to tell TCP which application on this host is supposed to have this. And because it's an email, and because the TCP port is going to be the email application port, it will give it to that application. The application will read the SMTP header, and it will give the data, the email, to the application, to the user, so I can read it. This would be 1 and 2 OSI module, layer 1 and 2, the frame. This is layer 3. This would be, in my book anyway, 4 and 5. And this is 6, 7. And this is your data, whatever subject you want. Checksum at the end is the layer 2 checksum. This is the way it works in TCP/IP. This is OSI, same thing. We don't have all of the headers. Some routing protocol, for instance, don't use TCP. In that case, OSPF, for instance, have an OSPF header and some OSPF data. Doesn't use transportation layer because it's built into OSPF. It's built into the application itself, in that case, routing protocol. So it depends on what application you're running. It depends on, obviously, compared to OSI, whether it's TCP/IP or not. If it's TCP/IP, this is more or less it. Any other thing, because remember that OSI was built to work on all datacom, not only TCP/IP. IPX, AppleTalk, DECnet, all of the protocols, it's built to create a structure of how you send data over a network. So whether I use the specific headers or not depends on the protocol and depends on the application. If it's IP, there's going to be an IP header. I can guarantee that.
The standard is a way of structuring data.
That's what the OSI is. Yeah.
Is it always additional information about the integration between layers, how that should be working?
Don't think I understand the question.
I guess you have some kind of interfaces.
Between the layers.
Yeah.
Yeah.
And the standard, does that also describe
Yeah.
how those interfaces
Yeah.
work?
For instance, in the IP header, as you will see later, one of the fields in the IP header is a field called protocol. The protocol field is going to tell IP layer that it's TCP that wants to have this. So if in the protocol field, if it says 6 here in the protocol field in the IP header, IP knows, okay, protocol number 6, I'm supposed to give this to TCP. And I'll give it to the TCP process. And the TCP process will look at the TCP header, and in the TCP header, there's destination ports. And the destination port is going to tell TCP what application is supposed to have this. And TCP is going to do his bit, and then they're going to give the data to the application. Yeah. So layer 1, physical layer, hubs, cables, wires, wall jacks, contacts, RJ45s, UTP cables, fiber cables, anything physical. Layer 1, how to send a bit. For instance, a hub. Layer 2, how to send a frame over a link. Could be an Ethernet frame, could be token ring frame, could be another kind of frame. Sending a frame over one network. Not between networks or from one network to another, within the same link. Sending Ethernet frames from one Ethernet to another Ethernet station, with nothing in between. Layer 3 is connecting networks. So sending data from one network via X number of routers to whatever networks I want to go to, where the hosts I want to go to are. So network addressing, IP addresses, all networks. The routers is responsible for keeping track of the networks and how to route to those networks. Layer 4, sending data between applications. So from one application, for instance, a file client, FTP client, from the client to the file server. So connecting applications together. Layer 5 is setting up those sessions between those hosts, applications. Layer 5 is Layer 6 is presentation. How do I present the data? Some encryption is done on this layer as well. Could be done on this layer. Depends on application. And then the application layer itself, where the user and the application has possibility to interact with the network. It might be your email application, your web server, your web browser, whatever it is. Now, if you want to compare, as I said, if you want to compare the generic OSI module with the TCP/IP's own module, this is more or less how they compare together. So layer 1 and 2, physical and data layer in OSI, in TCP/IP and the TCP/IP module, it's called network access layer. There is no TCP/IP protocol down at layer 1 and 2. But TCP/IP needs somewhere down. It needs to be something down there. Remember we said earlier, an IP packet needs to go into something else. Could be Ethernet, token ring, or whatever. Something down there. It's called network access by the TCP/IP layer. Layer 3, called network in OSI, is called the internet layer in TCP/IP. This is where IP, the protocol IP, works. This is where we have IP addresses and IP networks. layer 3, connecting networks together. Layer 4 and layer 5 is the so-called host-to-host layer. It's where TCP or UDP, the transport protocol, works, connecting hosts together and applications on hosts. And the top layer, layer 6, layer 7, is the process layer. Now, this is the way I would have done this if I've done this slide. I didn't. Now, if you read some books or if you look at, listen at some other instructor or something, it might be that some say that the process layer is 5, 6, and 7, and that the host-to-host is only layer 4. And that has to do with having something that is generic, the OSI module, trying to fit into something that is a actual working implementation, which the TCP/IP stack is. Because it's all generic OSI, the boxes don't really fit. So you have to squeeze them a little to make them fit into the other boxes. So when you do that, some squeeze one way and some squeeze another way. I like this squeezing better than the other squeezing, but there you go. You read some other book, and I say, well, host-to-host is only layer 4. So, but this is the way I think it's best. The TCP/IP module, by the way, is also called the DOD module. DOD stands for Department of Defense. The American Department of Defense was a big part of ARPANET in the beginning. So they were also a big part of TCP/IP in the beginning. So just to summarize it, you got the LAN and WAN technologies down at the bottom, token ring, Ethernet, ATM, frame relay, whatever, layer 1 and 2. On top of that, we're running IP with some of the IP protocols. We'll go through ICMP and ARP, for instance.
ICMP, ARP, etc., they are not having IP on top of it. They are trying
ICMP, for instance, is using... So if I would do this, ICMP has an IP header, and then there's the ICMP message inside. Whereas ARP, which is in this slide actually written in at layer 3, ARP isn't using IP at all. So ARP would be no IP header. It's a layer 2 header and a checksum. So if I would have done this, I would have put ARP down at layer 2. Whereas ICMP is actually using IP, so but yeah, some of them are, some of them not. Reverse ARP is the same thing. EGP, which is basically dead, I don't know why it's in there, and OSPF are routing protocols, just using IP as well, but I would put them higher up. So layer 3, IP, and some of the protocols. On top of IP, in the TCP/IP world, we run either TCP, which is connected-oriented, we'll go through that later on, and UDP, which is connection-less, host-to-host or transport layer protocols. And on top of those, all the TCP application protocols. HTTP for surfing, SMTP, as we said, for sending mails, FTP for file transfers, telnetting for doing configuration on remote devices. SNMP is simple network management protocol for doing management. TFTP is trivial file transfer protocol, and so on. All of those TCP/IP protocols, which reminds me that I probably haven't told you, TCP/IP is the name. TCP/IP is the name of the protocol suite. And in the protocol suite TCP/IP, there are lots and lots and lots of protocols. And every single day there gets extra protocols in there. So when you say TCP/IP, we're talking about the protocol suite TCP/IP. Now, two of the biggest ones are TCP and IP. That's why we call it TCP/IP. But in there is lots and lots and lots of protocols. All of them. Those are just some of them. And it gets more and more every day. Lots of protocols today. Questions on the OSI module?
In a typical frame,
Yeah.
what proportion is the actual application data and how much is all these headers in the assembly?
It's a really good question. It all depends on the application, obviously. For instance, if you're sending voice, your typical voice packet isn't much data, but you will have all of these headers. So you will have a lot of extra overhead for sending voice, for instance. It's much, much, much more efficient to send voice over an E1 or something. You don't get the same kind of headers. If you want to do voice over IP, you're going to end up with all these IP headers. So, no, it's a typical voice packet is at the most 20 bytes, something like that. And you have a header. This is 14 bytes at least. This is 20 bytes. If it's TCP, it's another 20 bytes. If it's UDP, it's another 8 bytes. And then you might have your IP application, some header, and then you got your data, and then you have 4 extra bytes at the end for layer 2 checksum. All of this to send at the most 20 bytes of data, the actual voice at the most. So lots of extra overhead.
For file transfer, there is a training process some of the protocols you can.
For the file
transfer.
Yeah.
Is it FTP that has size of the, or is it TCP that takes the
The size limits. I mean, there's different kinds of limits here. If it's Ethernet, for instance, the Ethernet frame can't be bigger than 1500 bytes.
But it's smaller when you have bad channel and larger when you have good channel.
That depends on the application in that case.
It's TCP that adapts to...
TCP adapts. Yeah, TCP adapts to the segment. It depends on lots of different things. If it is TCP you're using. In FTP case, it is TCP. And TCP does adapt. It does also adapt to the receiver. How much data can I send and how much data is actually getting through and stuff like that. So TCP will adapt. A TCP segment could be really big. An IP packet could also conceivably be really big. 64K if I want to. Now if I do IP packets that big, then it's not going to fit into the Ethernet frame, so we don't, basically, but we could if we wanted. All right? We need a break. Or should we start with the next chapter? All right. Small break. Are you tired? The hour after lunch. The instructor nightmare hour. 2:30. All right. Everyone's awake? No short today either. I don't want to throw the pens on you. So. All right. The next chapter, or actually the next 2 chapters, is about IP addressing. So we'll go through IP addressing and what's the subnet mask and how it all works. And now, usually when I do this, it takes about 3 hours. Just so you know. And I don't ever use the slides. Now, because we're filming this, we need to use the slides. So bear with me if I look confused, because I never look at these slides usually. What do you know about IP addressing? How to reach from A to B. So network addressing, how to address a host and another. Yeah? Anything else?
There is public addressing, private addressing.
There's public addresses and private addresses. We'll go through that later, yeah? Anything else? How big is it? The IP address. We're talking IP addressing now.
IPv4. It's different.
IPv4, yeah. We might discuss IPv6 if we got the time, which we probably won't have. So, IPv4. How big is address? 4 bytes, 32 bits. I'd rather say 32 bits than 4 bytes, but right. Anything else you know about IP addressing?
A and B and C.
Good. All right. So now we agree on the IP address being 32 bytes big, 32 bits big. And we also know about classes. Class A, B, C, D, and E. Now these ones, A, B, C, is the one that is interesting at the moment. Class D is for multicasts, IP multicast addressing, and Class E isn't used. It's experimental. All right. The one thing that I think is most important in understanding IP addressing is this, basically. An IP address, 32 bits long, always has 2 parts. One part is the network. It will tell me what network I'm on. The other part is the host. It will let me know on that network which host am I. The same thing as in your friendly neighborhood. I got one part telling my the street name is telling me what street I'm living on. And my house has a number to let me know what house on that street is my house, so that the postman can deliver the mail to my house. Now, if I'm living on the same street as anyone else, we'll have the same street address. But every single house on that street is going to have its own number. And it's exactly the same thing with IP addressing. If I'm on the same network as someone else, my network part is going to be the same for everyone on that network. Now, on the network, just the same as houses need to have your own number, my host on the network needs to have a unique host ID. It wouldn't be nice for the postman if we live on Belmont Street and all houses have number 31. Where do I deliver the mail? And it's the same thing with IP addressing. If I'm on the same network as someone, we got the same network part, and then we got a unique host address, host part of the IP address. Now, in the beginning, this was really simple, because we got A, B, and C classes, and if I'm a class A, if I'm on a class A network, my first byte, an IP address 4 bytes, right? 32 bits. If I'm a class A address, I'll have a first byte between 1 and 126. If I'm on a class B network, I'll have first byte between 128 and 191. If I'm class C, I'll go from 192 to 223. So by looking at the first byte in an IP address, I can know whether it's a class A, B, or C address. Now, what's that used for? What were it used for? It were used to let me know, out of those 32 bits, which part of those 32 bits is the network part, and which one is the host part. So if I'm on a class A network, the definition is network host, host, host. So the first byte in a class A network is the network part. The other 3 bytes is the host part. We usually write IP addresses not at 32 bits because the human mind isn't very good at remembering 32 ones and zeros in a row. If I would say to you, my IP address is 111.000.000.111.100 and go on like that for 32 bits, you won't remember it. But if I called my IP address 192.168.0.5, chances are you might remember that. So we write IP addresses as something called dotted decimal notation. So 1 byte at a time with a dot in between. That's the way you usually see IP addresses, right? But an IP address is 32 bits. We as a human like to write it as dotted decimal notation with a byte at a time. If it's a class B address, they decided that if it's a class B address, it's network, network, host, host. And if it's class C network, it's network, 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 host. So how many different class A networks are there total whole world? 126 network 1, network 2, network 3, all the way up to network 126. There's only 126 class A networks total in the whole world. They're huge, enormous, because on every single one of those networks, I got 24 bits left to number my hosts. There's somewhere around 16.9 million hosts on a single network. Could you imagine having 16 million hosts in one broadcast domain? It's not that funny. There's only 126 class A networks total. They're enormous. There's 64 different values in the first byte in the class B address, and there's 256 different values possible in the second byte. So total number of class B network is 64 times 256. Somewhere around 23,000, unless I remember wrong. Now, out of C addresses, there's 32 numbers or values in the first byte, 256 in the second, and 256 different ones in the third ones. Since they all decide which network I'm on, there's 32 times 256 times 256 class C networks, around 2 million class C networks. So 126 class A networks, enormous. There is somewhere around 20,000 class B networks with 16 bits on. You could have 65,534 hosts on those networks. Big network still. And there are lots of class C networks, around 2 million. But you can only have 254 different hosts on there. Remember that IP addressing is from the middle of 70s, early 80s. When they did this, they actually thought that this was good enough. 126 really big networks. Why do we ever need more? And 20,000 quite big ones, and 2 million class C networks. That's a lot, right? Now, on an internet basis today, nope, not good enough. But this is what they thought was good enough. They didn't know what we know about the internet. back then. Now in this case, IP address is really simple. I will look at the IP address. I will check the first byte. If it's a 126, I know that the divider between the network and the host is after 8 bits. So just to give you some examples, this IP address those two IP addresses, are they on the same network? Yes, they are. First byte says 10. 10 is a Class A network. If it is a Class A network, which it is, the first byte is the network one. Is the network one? Is the network part the same? Yep. If the network part is the same, we're on the same network, right? That's what I told you previously about the street names. We've got the same network, we're on the same network. Same or different networks? Different network. 172 says Class B. Class B says network, network. Network part is the two first bytes. Are they the same? Nope, not the same. Since the network part is not the same, we're not on the same network. All right? Same thing with Class C. One more. 194.10.10.7, 194.10.11.4. Same or different network? Different network. 194 is the Class C network. The network part is the first 3 bytes. They're not the same, so we're not on the same network. All right? Now you know everything you need to know about IP addresses in the 80s. Yeah. Sorry. Who owns it? These are owned by, or owned. These are used by big companies that were big in the 80s. So IBM, General Motors, NASA, universities, stuff like that. They don't. They've been allocated that back in the good days, and they won't return it for obvious reason, because they're using that in their own environment, right? Now, if they're supposed to return these addresses, they're going to have to reconfigure about 2 million hosts or something like that. So we don't want to return them. We do want them to do it, and they're actually doing it, some of them. But someone has to pay for that because it's not cheap. So if I got an A address, I might use it. But there's only 126 Class A addresses. And also, I haven't told you, but 120, it's actually from 0, but we don't use 0. And it's all the way up to 127. We won't use 127. I'll tell you why in a minute. This is all the addresses where the first bit in the first byte is 0. That's where the Class A addresses come from. The most significant bit in the first byte, if it's 0, it's a Class A address. If it's a 1, it's the other ones. So in 126 Class A networks, half of all IP addresses in the world, including the ones we don't use for networking or host addresses, multicast and experimental ones. Half of all IP addresses are in 126 Class A addresses. Lots of addresses. So you can now understand that since we don't have lots of addresses, why we want these back. If I got a Class A network, if I, as an organization, have a Class A network, I'm owning 1/256 of all IP addresses in the whole world, including the one we're not allowed to use. So lots of addresses. What's the 127? Anyone know? It's not used. Local host. All PCs that has an IP stack, you can always try to ping 127.0.0.1. So local host. It will answer if the IP stack is working. So someone said, we need an IP address that is the same. It's always my IP address. And say, okay, let's take one Class A network, the 127 network, we don't need that, and we'll make that into local host. That's really stupid, because we're throwing away 256 of all IP addresses, because we need an IP address on every host, local host. Not really smart, but they didn't know that back then. So the IP address structure, we got network part and we got the host part. For instance, 16, 105, 26, 3. The bits, the binary bits, 128. This is the value of the bits in a byte, if you haven't seen this previously, depending on the position in the byte. A bit can only be 1 or 0, right? A bit is either on or off, right? Now, depending on the position the bit has in the byte, it has a value. These are the values for the bits, depending on the position in the byte. I won't go into the maths, I do that usually, but not today. We'll skip the math part of it. You can do that on your own if you want to. Calculating between binaries and decimal. Hex is also fun. Now this is the class of networks. And as you can see, class A networks is 0 in the first most significant bit in the network part, in the first byte. And the rest could be whatever. So between 1 and 126. Class B address is 10 in the first byte, which gives us values between 128 and 191. 2 bytes for networks. And Class C, 110, the first 3 bits, which give me values between 192 and 223 in the first byte. The first 3 bytes are network bytes in Class C addresses. Some of the addresses is reserved. For instance, 0000, which is the I don't have an address. If you have a PC running, which we'll talk about later, DHCP, for instance, and you don't get an IP address, it will show up as 0000. I don't have one. The loopback address, we talked about that. 255.255.255.255 is the broadcast address, IP broadcast address. Generic, if you like, broadcast address. And then on all networks, or as we will talk about later, subnetworks, there is 2 addresses that can't be used. The first one, the one with all host bits are 0. All host bits are 0. That's the network itself. It's what I'm using to tell you that it's this network I'm talking about. Can't use that for IP hosts because it's the network address. The last address in all networks, the one where all host bits are set to 1s, is the broadcast address on that network. It's that network's broadcast address. So on all networks and subnetworks that you create, the first and the last address can't be used. It's the network and the broadcast address for that network. Okay? Anything in between is okay. Now we're running out of film. All right. Let's take a break, and then we'll start with the private addresses.